Okay, today we are exploring the comprehensive systems engineering architecture framework. Our goal is to trace how high-level abstract requirements seamlessly transform down into concrete physical realities, meaning we take pure software, math, equations and code and turn them into actual manufactured silicon chips, copper circuit boards, physical metal enclosures and working hardware. Let's look at how we systematically bridge all of these layers together. We begin at level 1 by setting operational boundaries like voltage thresholds, power profiles and thermal limits. Regulatory frameworks like FCC and CE compliance are anchored right here at the conception phase. Simultaneously, mathematical models form the behavioral backbone, using continuous and discrete transformations. We use, for example, Laplace and Fourier domains alongside PID loops to guarantee stability before any physical hardware is built. Moving into level 2, we split into core tracks. In digital design, we configure programmable FPGA logic and embedded microcontrollers, while high-speed bus standards like PCIe and DDR ensure high bandwidth throughput. Parallel to digital, we have analog electronics, which handles signal conditioning and precise power management, with switching regulators and data conversion blocks bridging real-world sensor data with digital computation. For wireless and high-frequency communication systems, RF or radio frequency and microwave engineering play a critical role. We design active LNAs, which are low-noise amplifiers, and power amplifiers, alongside passive microstrip circuits and matching networks via Smith charts, where antenna placement and phase arrays dictate the final radiation performance and connectivity range. At level 3, we move into physical implementation. Schematic capture turns into multi-layer PC board stack-ups, meaning printed circuit board stack-ups, where controlled impedance and trace length matching are enforced to prevent signal integrity degradation. But hardware isn't just electronics. It requires robust mechanical housing and electrical harnesses or looms. Thermal heatsink path and structural packaging protect components from physical and environmental stress. Before fabrication, we run exhaustive SPICE circuit simulations, which stands for Simulation Program with Integrated Circuit Emphasis, and 3D electromagnetic solvers at level 4 to catch EMI, or electromagnetic interference, vulnerabilities and timing bottlenecks early in the development lifecycle. Finally, physical hardware bring-up, which is that critical first moment we power on a newly manufactured board to test and wake it up. Uses lab tools like oscilloscopes and spectrum analyzers. We close the loop by verifying empirical performance against our initial level 1 blueprint requirements. To wrap everything up, let's look at how these 4 levels come together as a complete life cycle. At level 1, we focus on system definition and modeling. This is where we establish our foundational design requirements, set operational and environmental limits, lock down compliance frameworks like FCC and CE, and build out our mathematical and algorithmic models using tools like Fourier transforms and PID loops. Next, at level 2, we move into multidisciplinary design. Here, we branch out into digital systems engineering with FPGAs and embedded processors, analog electronics for power management and signal conversion, and high-frequency RF and antenna engineering for wireless communication. Moving to level 3, we enter physical implementation and integration. This is where schematics turn into multi-layer printed circuit board layouts with controlled impedance, and where we build out the mechanical housings, thermal heatsink paths, and electrical harnesses to protect the hardware. Finally, at level 4, we complete the loop with prototyping, simulation, and validation. We run SPICE circuit and electromagnetic simulations before fabrication, power on our boards during hardware bring-up, using lab tools like oscilloscopes, and perform final functional verification to ensure everything matches our original level 1 blueprint. Okay, I hope you find this helpful.